Oh yeah, people are starting to flow in now. Okay, I see some of the graduate students are online. Some of our faculty are here. I see some guests. Okay, welcome everyone. Let's just wait a minute and then we'll just, there are more people coming in, I see. Okay, well, I'll just start with the introduction since my part is not that important. Well, welcome to the physics seminar series supported by Eddie and April Lucas. Today's speaker is Gerald Jackson, who's a NIAC NASA fellow. But more importantly, Holger Meyer and I have known Jerry for a very long time. I've known him since he designed the KTEV beamline at Fermilab, since Jerry was one of the youngest fellows of Fermilab ever, and he became a permanent staff scientist there. I guess now retired from Fermilab, but still keeping active in the world of antiprotons. And his talk today is about deaccelerating interstellar spacecraft utilizing antimatters. So everyone, please join me in welcoming Jerry.
Thank you very much, Dick. Okay, so today we're going to talk about interstellar voyages of unmanned probes, and the destination is Proxima Centauri. So Nick already went through this, basically my background at Fermilab and so on. By the way, I'm not retired. I was actually drawn away from Fermilab by a private company that offered me almost double the salary Fermilab was offering me. So I went for the money. Okay, so what we're talking about here is a unmanned scientific probe composed of two stages. An acceleration stage that gets you up to some fraction of the speed of light. We'll discuss what fraction that is. And then a deceleration stage that slows down a 10-kilogram instrument package so that it could go into orbit around the habitable zone planet Proxima B, and then provide decades of propulsion and power for the scientific instruments and communications to and from Earth. So one of the things that we're looking at, it's very different, is having the ability for Earth to upload updated instructions to the spacecraft all the way over to Proxima Centauri. So the propulsion and power systems are based on antimatter-induced nuclear fission of depleted uranium, and we'll go over that a little bit more. And then both stages are capable of deploying up to 1,000 1-gram scales chipcraft to perform auxiliary measurements or to actually enter the atmosphere of the planet or to do other specific operations. For those of you who are old enough and remember Speed Racer, it's the little drone that would come out of his car and help him out when he was running his car races. So, both stages are tasked with performing early scientific discovery missions so that you don't have to wait for the 50, 100, 200 years it takes to get to Proxima Centauri. You could actually start getting scientific return from the mission within 5 years of launch. So right now, there are really two basic proposals that are being pushed. One is what I'm doing here with an orbiter where we slow down at Proxima B. The other, which you heard about a few weeks ago from Professor Lubin of Santa Barbara, is a directed energy beamed spacecraft that is launched from the Earth solar system and then just flies ballistically to Proxima B. Now, each of them have different advantages and disadvantages. And I'm not going to read through all these. I mean, you can read them on your own, especially since this is being recorded. You could go back and pause the playback later. Basically, what we're doing is we're trading off what each side considers to be either a difficulty or an advantage. So in the case of the breakthrough starshot, the flyby, what they're proposing is something they think can happen very quickly and at a very high speed. So they're claiming 20% of the speed of light and something they could start almost immediately. They're trying to get this funded now. Okay. For the orbiter side, the trade-off is we want to do actual science. So we want to actually do persistent measurements instead of just flying by and taking 2 frames, 2 pictures, and then taking 10 years to transmit the images back because you only have 5 milliwatts of power on board their shipcraft. What we're looking at is spending decades there, getting updates from Earth, actually doing robust science. And then the cost of that, of course, is you have to figure out how to slow down the spacecraft. And so those are the 2 approaches. And each side will claim that their strengths and dismiss the other's weaknesses. So one of the reasons that I prefer the orbiter approach is the fact that the realities of sending chipcraft across this interstellar void and making it to that solar system, and then being able to take a picture at the right planetary phase, and let alone pointing the camera in the right direction, is non-negligible. Okay, and so for instance, you see our solar system in the upper left here, and you see Mercury, Mars, Earth's orbit, and the relative distances there. In the bottom left corner of that figure, you see that little yellow spot, which looks like the sun. That is actually the orbit of Proxima b. So you're actually trying to hit a very, very, very tiny target, okay? Plus, as you see from the picture of Mercury to the very right from Earth, when you are outside of the orbit of the planet that you're observing, you're always going to see a crescent because of the aspect ratio of basically the sun is always in the way of the measurement. For instance, Hubble has never taken a picture of Mercury or Venus because of the light load from the sun would distort the optics, and they don't want to destroy the telescope. So in order to really get a good image of Proxima b, you really want to fly between Proxima Centauri and the orbit of the planet at the correct phase so that you can actually see a disk instead of just a small crescent. So this is basically the geometry for what I'm proposing. So we have our solar system on the left, the Proxima or the Alpha Centauri star system, which is actually a trinary star system to the right. They're separated by roughly 4.3 light years. And we know we have an Oort cloud, though we don't have a direct measurement of it yet. But we're theorizing, since the combined mass of Alpha Centauri A and B is about double that of our sun, that there should be a comparable Oort cloud around that AB binary system. And because Proxima Centauri orbits are so far away from the binary, the close-in binary, it's probably orbiting either within that Oort cloud or has already disrupted that Oort cloud because of its gravitational influence. So either way, that would be an interesting result to measure. So what we're proposing is that during acceleration, so we're assuming a 10-year acceleration period and a 10-year deceleration period, and then an interstellar drift, that there are many destinations or science missions that you can pursue during that voyage. So you're passing through the heliopause within a year. You're passing through the Kuiper Belt in under 3 years. You're in the our Oort cloud between 5 and 14 years. There's the local interstellar cloud. There's a G cloud. You can measure the interstellar magnetic field. Then you have the Centauri Oort cloud. And one of the things we're looking at in our NIAC proposal is that the acceleration stage, it continues, the deceleration stage, the B stage, will start slowing down, but the A stage, the acceleration stage, keeps going at the interstellar drift velocity. And so one of the things that we looked at doing is deflecting its trajectory a little bit so that it does a flyby of the AB binary system. And then, of course, then Proxima B orbit with the decelerator. So this architecture of trying to do early science is very similar to what was done with Voyager 2. In Voyager 2, you did the grand voyage where you passed by Jupiter, then Saturn, then Uranus, then Neptune. And all of that took about, 12 years, within 12 years of launch. And then there was this very, 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 very long delay until very recently when Voyager 2 passed through the heliopause and started sampling the interstellar medium beyond the solar bubble, magnetic bubble. What we're proposing is basically the same approach. So we do all this early physics like the Oort cloud objects and the interstellar medium and the G cloud and so on, while we're waiting to get to Proxima B. So in terms of logistics of how do you pull off a mission like this, a good historical parallel is the Apollo moon landing. So as most of you know, that happened in 1969. The goal for that was set in 1961, so that was 8 years of advance notice to get there. And then the technology development took 20 years before the lunar landing, and that was motivated by the World War II and work done at Pelamunda and V2 rocket and all that sort of stuff. And then the post-war work at Huntsville. Of course, Kennedy, his goal wasn't just science either. It was the space race and beating the Soviet Union and so on. So there were other priorities that pushed the discovery phase of landing on the moon. And then, of course, the beginning of all this was Robert Goddard, who patented staging in liquid fuel rockets in 1914. And he also worked on gyroscopic guidance. So really, it took 55 years from when you had the basic ideas made public to when the moon landing could actually occur. So right now, we're basically envisioning the same sort of timeline where I'll be long gone before this mission ever launches. But in the true spirit of science, where you shouldn't always be looking to get make progress in your lifetime, but to set the stage for future generations. That's kind of the approach here. So very quickly, one example of a early discovery mission is taking a census of Oort cloud objects. So measuring their size distribution, their spatial distribution, their radial distribution, their velocities, their charge states, the effect of cosmic rays on emissions from these Oort cloud objects. All of this science is one of the things that we're looking at right now, whether we can actually accomplish or not. So it turns out that antimatter is very hard to make, as everybody probably knows, and therefore you want to use as little as possible. And so if you look at the amount of antimatter needed to decelerate a 10 kilogram spacecraft, dry mass spacecraft, as a function of the voyage time between Earth and Proxima B, you see that the antiproton appetite goes as the inverse square of the voyage time. So you use about less than a tenth of the antimatter for a 200-year mission than you would need for a 50-year mission. So there is a reason for wanting to go slower. It also makes some of the intermediate science easier to perform. You're still getting all of the early science that is already would justify the cost of this mission. And then very far into the future, similar to the heliopause science that's being returned from Voyager right now, 200 years from now, you would get the science returned from Proxima B. So that's kind of the stage. Okay, this very briefly, just put this up. This is all the things that we're working on during our NASA proposal that was funded in June. So let's look at antimatter propulsion. So if you have a 10-kilogram spacecraft and you want to slow it down, you don't want a propulsion system that is 200 metric tons. You want a propulsion system that is on the order of 10 kilograms or less. Okay, otherwise the propulsion system, you're spending all the energy slowing down the propulsion system, and the spacecraft instruments are just a flea on the back of a dog, right? And you really want to try and find a way to make a very lightweight propulsion system. So this work started in 2002. It was also funded by NIAC, but it was only for getting outside of the heliopause of our solar system. It had that study did not look at interstellar travel. And similar to the early study, we're still using uranium-238, so there's no highly enriched uranium out in space. They're not launching dangerous materials, so on. Unfortunately, the original propulsion design was very inefficient. There was no way to produce a collimated exhaust thrust, so fission daughters are going off in every direction. And there was a limited dry mass to fuel ratio. And we did not yet come up with a way of storing antimatter for long periods of time. So this was all corrected in around 2018 and beyond. So this is the architecture that we're now dealing with. So for instance, if you look at the figure there, we have a spacecraft to the lower left, and then there are these two what look like parachutes. Those are very, very sparse wire grid electrodes. And what we're doing is, okay, the fission events are occurring at the apex of the inner blue parachute. So what happens is that we're producing fission. The fission daughters come off, and they are electrostatically charged. That's been measured about a charge of 20. And so and at a MeV per nucleon. So what you need is about a 5 MeV or 5 megavolt potential difference between the two sails. And if they're shaped relatively parabolic, they're not exactly parabolic, but close. What you get is both fission daughters are turned around and come out in a fairly collimated exhaust stream. And so the MeV per nucleon corresponds to about a 4% of the speed of light. So you're ejecting your reaction mass at 4% of the speed of light. That means you can get up to 5 or 6% of the speed of light for reasonable mass ratios of fuel to dry mass ratios. Now, how do you produce these fissions? Instead of sending antiprotons into a solid target, what we do is we have something that looks very much like a penning trap, except this is purely electrostatic. And for those of you who say that's impossible, ask why the Tevatron Collider at Fermilab was able to store antiprotons, yet it was purely magnetic. Okay, and the reason for that is because the antiprotons were moving inside of a lattice that was spatially changed gradients as you went around the ring. In this case, you have an electrostatic lattice that is focusing it focuses and defocuses periodically as the antiproton sloshes back and forth left and right across the trap. And so in that case, you also get strong focusing, similar to you get in conventional magnetic storage rings. So in this case, because it's electrostatic, it's very lightweight, and it's possible to store ions of uranium, and then what you do with a comparable potential, you pass back and forth antiprotons at the same velocity traveling in the same direction. And when you do that, you get your standard DDX, so the antiprotons slow down with respect to the depleted uranium ions, and eventually displace an electron, are captured, cascade down because they have different quantum numbers from the orbiting electrons, and therefore annihilate against the nucleus and induce fission. So it turns out that for depleted uranium, basically 100% of the antiprotons that are captured and come into contact with the nucleus induce fission, regardless of the isotope of uranium. So here is a close-up of these trajectories from the fission daughters coming off and being deflected by the electric field between the equal and opposite charged inner and outer mesh electrodes. We've already done an estimate of the mass of such electrodes and the size needed to stand off 5 megavolts and so on. And it comes in at around 1 kilogram. So in that sense, mission accomplished. Also, the trap for inducing the fission, it looks like it's under 1 kilogram also. I mean, of course, we remove a lot of weight because we don't need a vacuum chamber. Okay, so what we find is that we have a low mass propulsion system. We have a low mass fission induction system. And if we have a very thin foil at the apex of the outer mesh electrode, by reducing the voltage a little bit, we can have some of the fission daughters transport their charge across and actually charge up the outer plate and hence create onboard electrical power. So we can provide up to 1 megawatt of onboard power while the propulsion system is driving the spacecraft. And of course, there's an alternative architecture where you make these spherical, and even without propulsion, you could generate power. So Fermilab, when it shut off its anti-proton protection facility, was making a little over 2 nanograms per year of antiprotons. And to enable a mission like this, we need to produce about 20 grams of antiprotons per year. So we need to increase the production rate by about 10 to the 10th. Okay. Now, if you look at the history of accelerator physics and you look at beam intensities, you look at beam energy, you look at many different parameters, the progression of those accelerators follows a curve which is very similar to Moore's law, where there's a doubling time every few years. And so over the history of accelerator physics since the 1920s, 30s, 40s, you've seen a tremendous improvement in all those parameters. And so what we asked is, can we get on a similar Moore's law curve for the production of antimatter? And so we looked at many different mechanisms for achieving this. So for instance, here is a good example of Fermilab. This is the Tevatron luminosity. The design luminosity, when I started there in 1986, the design luminosity was 1, actually is 1 times 10 to the 30th inverse centimeters squared inverse seconds. But at the time, because CERN and other laboratories never met their luminosity goals, there was a lot of doubt whether Fermilab could ever achieve 1, the design luminosity. In the end, it turns out that Fermilab achieved 500 times that design luminosity. The early improvement rate, when we were just making improvements to subsystems, was a factor of 10 every 5 years. And then later, when we started doing civil construction, built the main injector, built the recycler ring, started doing harder things, and then also had to upgrade the detectors, the CDF and D0 detectors. Then that order of magnitude increase lengthened from every 5 years to every 12 years. But the point is, if you keep the scale of the accelerators and the improvements small, you can actually have a very rapid progression in luminosity or in production rate. So at Fermilab, what we did is we took 120 GeV protons every 1.5 seconds, slammed them into a nickel target, and for every million protons on target, we got 15 antiprotons out. And this was for 120 GeV beam. And the mechanism basically was that you basically formed PP bar pairs with the excess energy. So here's a picture at the bottom of the target and then the accelerator complex needed to achieve all this. So at Fermilab, at the end of the collider run, there was a proposal to use a thin target rather than a thick target to produce the antiprotons. This allowed one to remove the scattering of the antiprotons as they went through the rest of the nickel target. And so that improved the beam density as it left the target. The problem with that approach and the whole motivation for Fermilab was you wanted collider beams to collide protons and antiprotons. And that required a very high, what's called longitudinal phase space density. Turns out that is a very severe constraint on antiproton production. For fuel, if you want to make fuel for an interstellar mission, you don't care about that longitudinal phase space density anymore. And so that removes a huge impediment to making more antiprotons. So what we did is we looked at other approaches, and right now what we're centered on is colliding two proton beams together. Now, to make it simple, the picture at the top shows two equal energy proton beams colliding. In reality, you wouldn't do that. You'd have a high energy ring, a low energy ring. And so instead of the collision occurring in the center of mass frame, the collision would occur in a boosted frame so that you would have a collimated antideuteron beam afterwards. So the idea is, antiproton beam. I'm getting ahead of myself. So what you want to do is you want to have the antiprotons produced in a small enough cone angle that you can capture all those antiprotons and cool them into a coherent beam. And so what you really want to do is you want to have an asymmetric collider configuration. So we've looked at this and looked at the accelerator physics of, first of all, you're not at 120 GeV anymore. You're at 1.9 GeV. So instead of using five accelerators, circular accelerators to produce the 120 GeV proton beam, you can actually just use one or two LINACs, superconducting LINACs. So it turns out between a threefold increase you get from not having a material target anymore, and then the sevenfold increase in moving away from all these ramping circular accelerators and going straight to a superconducting LINAC, you could achieve, at least on paper, you could achieve your 10 to the 10th improvement production rate. So how much would this cost? So when you're building a facility, there's two costs. There is the capital cost, the cost to build the accelerator complex or the factory, the fuel factory, and then there's an operational cost. Now, for instance, in the Breakthrough Starshot, one of their advantages was that the launcher could be reused to launch thousands and thousands and thousands of chipcraft. Okay, so it's a one-time investment. The same could be said for the antiproton facility. Once you build it, it's done, and no matter how many missions that you fuel afterwards, you've already paid for the capital cost. So really what then comes into play is the operational cost. So if you're producing 20 grams of antiprotons per year, how much is your electrical bill, basically? And so this chart shows such a calculation, and you go through all the numbers. I'm not going to go through each number right now, but basically, assuming 100% efficiency, which in accelerator physics, 70% efficiency is pretty normal for klystrons and other sort of electromagnetic accelerator structures. So the theoretical cost is about $670 million per year. Now, this has a lot of assumptions built into it. For instance, the price of electrical energy and so on. But $670 million a year is a lot smaller cost than you'll see from critics of this plan who say that if you just take Fermilab, the cost of Fermilab, which is basically $1 million a day for the electrical power, and or you look at CERN and then just scale the 2 nanograms and then scale that to 20 grams, you know, you get the gross national product of the entire planet for 1,000 years. Okay, but that doesn't make sense because neither CERN nor Fermilab were optimized for fuel production. Okay, they were optimized for high energy physics. So $670 million is actually not that much money. Turns out that's comparable to just mission control costs to receive the data from Proxima B, to analyze the data, you know, to pay all these people, to keep all the receivers going and so on. So the fuel cost is actually comparable to all the other costs in such a mission if you were to cost it out. So in the past, so how do you accumulate these antiprotons? Well, you're talking about we're talking about 35 grams. There's no way you're going to do that by storing individual antiprotons. So you need to form atomic antihydrogen. But then also you can't just store atomic antihydrogen. So you've got to produce molecular antihydrogen. The way, again, similar to the antiproton production at Fermilab or CERN, you would never use the antihydrogen formation techniques at CERN to produce fuel for a mission like this. CERN is trying to do atomic physics, they're trying to do CP violation, they're trying to do all these physics measurements where if you had too much, first of all, they don't even want molecular hydrogen, but even if they did, you would have too many molecules around and it would be harder to do the measurement than with individual stored antihydrogen atoms. So you need a completely different way of looking at this. And so over the last several years, we've been looking at this. So it really, the analogy is ion implantation of semiconductors. So what you want to do is you want to levitate a small piece of antimatter in the middle of a trap, and then you want to deposit antiprotons and positrons to accumulate more and more antihydrogen. Now, so what happens is the antiprotons and the positrons undergo DDX. They slow down. They heat up that target, and so depending on what that target is made out of, there's a thermal limit. So therefore, there's a rate limit and a kinetic energy limit to the beams. So you can go and first of all look at the materials. And so antihydrogen and antihelium, which are the same as hydrogen and helium, both have very, very high vapor pressures, even at cryogenic temperatures. So those are not candidates. The first quote unquote reasonable target material would be lithium, but it has a very low melting point. In fact, too low. Okay. And so really you want to look at, if you're just restricting yourself to the elements, you want to look at either beryllium or boron, or the best is carbon, okay? The problem is, how do you make, well, first, before we get into that, the problem. So if you look at the various materials and look at their accumulation rates, for instance here, if you're assuming that for each material, you're limited by their melting temperature and their the sublimation rates at a given temperature below that melting temperature, and looking at, you want to still, you want the sublimation rate to be a small fraction of the accumulation rate. So the question is, as a function of months of production, so while you're, during these months, the radius of your target is increasing. You're accumulating more and more particles. So so what would happen is that as the radius gets bigger, of course, your surface area gets bigger, your black body radiation power that dissipates some of that heat goes up. And so therefore, the maximum kinetic energy that the two beams could have going into that target increases as that target mass gets bigger. And so, for instance, if I had carbon ions going into a target, by month 10, I would be able to have 100 kilovolt kinetic energy for both the positron beam and the carbon ion beam coming in. Now, you don't have to restrict yourself to elements. You can also look at compounds. So for instance, lithium hydride is an interesting compound, and we'll talk about that a little bit more in a few slides. So, but okay, to make anti-lithium, carbon, any of these things, you need to make antineutrons. Now, forming a free antineutron is pointless. Okay, you can't capture it. You would need, sort of critical mass level or high cross-section atoms in order to capture these things. So it turns out that a much better production method is to produce antineutrons already bound to antiprotons. So the basic idea is to collide two antiprotons and make antideuterons. And so here is the cross-section in microbarns as a function of incident energy, where you have in this case, of course, all this data is for normal matter. So here you have a proton beam incident on a hydrogen target with an incident kinetic energy here of, let's say, 300 MeV or 305 MeV, okay? So, and it turns out 80% of the time you get a antideuteron, and then the other periods of time you either get a free neutron and a free proton. So basically the deuteron disassociates, or you get other particles. And so the idea here is, again, not looking at this from an asymmetric collider point of view, but from a very simplistic equal energy point of view, 270 MeV antiproton beams is sufficient to produce a antideuteron. And then, of course, with a witness pi minus. So again, we have our two storage rings, one a low energy, one a high energy. And so the idea is that you make the energy asymmetry large enough so that the cone of deuterons that are formed is small enough that you can capture all of them, cool them, and form them into a deuteron beam. Once you have your two deuterons, so that's the top of this plot to the right. Those are your two antiproton beams colliding, forming antideuterons. And now what we do is we take the antideuterons, split them into two beams, collide them. This is basically DD fusion, okay? So same cross section, same dynamics, same fusion products come out. 50% of the time you form an antitriton, and then you take another antideuteron beam, collide with the antitritons. So this is DT fusion. This is either, all the other attempts or thermonuclear warheads. I mean, this is standard DT fusion put in the antimatter world. So this has a 5-barn cross section, and 80% of the mass can theoretically be captured. And that forms anti-helium, so anti-alpha particles. So you take the anti-helium beam, collide that with anti-triton beam, and you get an anti-lithium 6 beam. That entire process has a theoretical mass efficiency of 27%. So that means 27% of the antiproton mass going into this factory for antinucleosynthesis will produce anti-lithiums. Okay, so why do you need this anti-lithium? Well, first of all, you can take your anti-lithium target, now hit it with some more antiprotons, and you could form anti-lithium hydride, which has a lower sublimation rate and a slightly higher melting point. So it's now possible to do some early production, maybe even lower rate production, but still you can do some early production with this target rather than an anti-carbon target. This anti-nucleosynthesis factory has a fairly high cross-section, so you can get reasonably high rates. But the trick is, how do you form that first milligram of antilithium, which is your target? Okay, and that's the hard part. But once you've made one, then you're home free. So basically the analogy here is sourdough bread production. Sometime hundreds of years ago, someone produced a bacteria or yeast culture that was able to take flour and make sourdough, right? So, and then you bake that and make bread. Well, it turns out because the yeast culture is alive, if you just keep feeding it water and wheat, you get more and more culture, and therefore you can make more and more bread. And so, you know, some of these bakeries are using the same yeast culture that they've been using for 100 years. And so the idea is that you do the same thing with the antimatter. And so once you get a target, you keep growing that target, and you use, for instance, maybe like laser to cut off little pieces and then replicate this factory so that you have multiple targets, and you can just keep growing this process. So really the sort of CERN complexity of forming your first milligram, you only have to do once. And then after that, you're home free. So one of the big problems that we had from the very beginning is, how do you store the antihydrogen? Because again, the antihydrogen has a very poor vacuum or vapor pressure. And so it turns out to store the antiprotons or the antihydrogen, you need a very good vacuum anyway, because you don't want outgassing from the surrounding vacuum chamber or the containment vessel holding the in this case, antihydrogen snowflakes or snowballs. You don't want you know, argon gas or other impurities that are coming out of the spacecraft surfaces to annihilate against our fuel, because by the time you get to your destination, the fuel's gone. Okay, so you needed a very good vacuum anyway. The problem is, if that vacuum is better than the vapor pressure, then you're going to get sublimation loss, and eventually you lose all your fuel anyway. So either way, you need good vacuums, but the good vacuum causes you to lose your fuel. So the answer, it turns out, is you want a containment vessel around the antimatter that prevents sublimation. Okay, so you can have your really good vacuum around that containment vessel so that you don't have normal matter interacting with antimatter before you need it. But on the other hand, you can preserve your antimatter. So it turns out the easiest way to do that is coatings. So this is used for foods and vitamins all the time, where, you know, particular vitamins taste terrible when you eat them. So what they do is they encapsulate it with a fatty molecule so that you don't taste it. And so by the time it goes down into your gut, that fatty molecule dissolves, and the vitamin is therefore available to be absorbed by your body. So the idea is, you have your antihydrogen snowball, and now what you do is you put a very thin coating of antilithium around that. So the antilithium basically acts as your vacuum vessel and allows the vapor pressure within that encapsulation to be in equilibrium, so that you don't have net loss of particles anymore. So the vacuum within the lithium is equal to the vapor pressure at whatever temperature that happens to be, whatever temperature the spacecraft surfaces happens to be. So we've done some studies, and it looks like about a 1 micron thick encapsulation would be sufficient. And so if you have a 27% antimatter mass efficiency for the antilithium, and you look at a typical snowball size, and then apply a 1 micron lithium layer to that, it turns out that the fractional mass of antilithium is very, very small compared to the antihydrogen. And so therefore that 27% antilithium production efficiency, mass efficiency, corresponds to a 99% overall efficiency. You just don't need that many antilithiums per antihydrogen. So the basic idea then is you have positrons, antiprotons coming in, you have blackbody photons coming out, you have molecular antihydrogen coming out. So you can imagine, for instance, something like a rocket nozzle shape where you have the antiprotons come in on one surface, you have the positrons come in from the outside. And now because this target is hot, the hydrogen is diffusing around within the material. It sees other hydrogens, forms molecular antihydrogen, picks up the positrons, and eventually you get outgassing of this of these or desorption off the surface of these antihydrogen molecules, and then you can have a low energy electron beam to ionize that and to suck it into your hydrogen, your antihydrogen snowball. So what we want to do an experiment. So it turns out if you want to do all this experimentally, everything I've been talking about so far, it's actually easiest to start at the end and work your way backwards. So for instance, if we took just normal hydrogens and formed a, took a cold finger and formed a hydrogen snowball around the cold finger, and then took a lithium beam and applied that to the outside, we could actually measure making an encapsulated snowball and looking at its sublimation rate. I mean, that's something we could do in the lab. It's not that expensive. Now, unfortunately, up until this recent NIAC funding, we didn't have the money to even do that. First of all, we couldn't afford the liquid helium refrigerator to get down to cryogenic temperatures. So I had a summer student, and we decided to do an analog of this, and that is to take sulfur and encapsulate it with aluminum. And it turns out that this is a good system to study. At room temperature, if you put sulfur in a vacuum chamber, your entire vacuum chamber gets destroyed by sublimation of sulfur onto the surfaces of the vacuum chamber, okay? So the idea is we made a sulfur slug, and then we basically took aluminum and bombarded the aluminum onto the sulfur to form an aluminum coating around that. Now it turns out, because the aluminum ions come in at very high energy with respect to solid sulfur, you get what's called hot atom chemistry. So you're forming compounds that you normally couldn't produce at room temperature. So in this case, you're producing aluminum sulfide. So there's an interstitial layer between the sulfur slug and the aluminum coating, which is this thin layer of aluminum sulfide in between. You expect the same thing to happen with the hydrogen snowball or antihydrogen snowball, where you're going to have an interstitial layer of anti-lithium hydride between the lithium layer and the hydrogen snowball. So this was our first experiment. It was a lot of fun. And this was an undergraduate from Alabama State University, or University of Alabama, Tuscaloosa, sorry. And then basically, if you want to continue these sort of experiments, what you would do then is put together a helium beamline and a Triton beamline and form lithium-6 beamline and basically work your way backwards. Every stage you go backwards, you go to bigger and bigger beam energies and higher and bigger accelerators, higher and higher costs. But the idea is that by having early successes and showing the feasibility of this, you can gather the funding needed and bigger and more funding as you go along. So as your technical risk is reduced, as your technical confidence goes up, the funding goes up commensurately until you get an entire facility where you're taking protons and making lithium-6 beams and cryogenically stored hydrogen snowballs with lithium coating And then at the very end, once you have enough money to make an anti-proton source, then you switch the polarities of all your magnets or all your accelerators. And now you could use the exact same accelerators and now do everything with antimatter rather than matter. So that's basically kind of the global plan. I have a few minutes left. So with your permission, I'm just going to go very quickly through another summer student project that's occurring right now. Plus, I have some help from some other collaborators. So the idea is, how do you actually observe these Oort cloud objects? So it turns out that, you know, it's very cold out in space, as you might imagine. And if you look at the solar irradiation as a function of radius, that's the black curve here, where that's microwatts per meter squared. So the sun's intensity on these Oort cloud objects scales, as you can see, drops off as you go further away from the sun, as you expect. Okay. Now, the red curve is the sum of that black curve plus the cosmic microwave background radiation. That's the 2.7 degree Kelvin background that's impinging on all objects out in space. Now, there are other contributors. There is the formation of crystalline ice. There is radionucleotides in the dust that are still decaying from the primordial origins. And you have the starlight from the other nearby stars. So there are a lot of estimates that say that you expect about a 10 degree Kelvin temperature, equilibrium temperature for deep space Oort cloud objects out at 50,000 AU at the outer edge of the Oort cloud. We're assuming much lower temperature for our studies here. And so, for instance, these are curves for the black body spectrum you expect from the microwave background, which is the red curve, and then a 6 degree Kelvin Oort cloud object with a standard albedo and everything else that goes into these based on comets, observation of comets coming into the solar system. And so what you see is that there are several orders of magnitude of contrast at terahertz wavelengths where we could, in principle, be able to distinguish an Oort cloud object's glow from the background cosmic microwave background. So in order to get enough photons to actually image a Oort cloud object like this, we need a big telescope, but we're still restricted down to, we want, you know, spacecraft to be on the order of 10 kilograms. So what the students are working on is building a telescope, a high quality telescope that is, right now we're looking at 2 kilometers, but eventually, not 2 kilometers, 2 meters, but eventually 6 meters of diameter that is under a kilogram. Okay, and so the idea is to electrostatically charge 2 surfaces so that they attract 2 films, so drum heads, so they attract each other. And if one of the surfaces has can have different voltages at different radii, so the blue disk to the left, each of those blue annuluses is at a different voltage. We can actually tune to get the shape that we need to get a good low aberration telescope. And so here is our first attempt. This was 0.3 meter diameter. It was about 0.5 kilogram, and we used a bicycle rim and just regular luminized mylar. And we were able to make it bow and form a spot. So this is still in progress, even though summer is over. The particular summer student we have from Iowa State University decided to take a gap year because of the COVID. So we now have some people that can work on this and see how far we can push this technology and how nice a quality mirror we can make. So with that, again, I'm done.
All right, thank you, Jerry. A little hard having applauses online, but we appreciate everyone's attention and participation. Jerry has some time for questions, I hope. Well, I'll take the opportunity to ask the first question then. This spacecraft, what kind of other power is it going to have with it?
Sorry, but power. I mean, there's electrical power. I mean, that's what you need, right? I mean,
yeah.
I guess well, I mean, okay, so we're emitting neutrons, so that actually is a potential probe, though at the distances we're talking about, the neutrons would decay long before it would actually hit an Oort cloud object or something. I mean, the density of material out there is 0.3 atoms or particles per cubic centimeter. So, I mean, it's even for very high cross-section atoms, it's very unlikely to do anything with the neutrons. But we are sending out lots of charged particles, the fission daughters. So there's something we might be able to do with that also. Probably the primary use of the onboard power, especially during thrust operations, is using the 5 megavolts, converting that into a laser light in the terahertz range so that we can illuminate Oort cloud objects or communicate back to Earth, or to do some sort of probing of the dust or whatever science we're trying to do. We would have a laser able to do that. And of course, the telescope is also going to be used to image the planet. It's going to be used to know the distance from the star, so we know when to start decelerating. A lot of these details, which we're already starting to worry about. Also computing. I mean, computing's a big energy drain on the spacecraft, which most people have not looked into yet.
But it's only a 10-kilogram spacecraft, so it has some limitations of what you're going to do.
Right. But and what you can do with 10 kilograms versus 1 gram.
Yes, of course. You can do a lot more with 10 kilograms than 1 gram. Okay, questions from the audience? I don't want to talk up all the time.
Feel free to unmute yourself and ask your questions yourself, or if you prefer, you can also type questions into the chat and I can take it from there.
Well, I see a blue hand for Bill Higgins, so why doesn't he go ahead and ask a question?
Hi, Bill.
Hi. I guess I was meaning to applaud rather than ask a question, but I really enjoyed the talk. Thank you.
I should point out Bill Higgins and I have known each other for a long time also.
Okay.
All right. Well, if nobody else wants to go, have you thought about applications for antimatter other than going to the stars? I mean, it's basically an energy storage technology, right? Are there any terrestrial applications where antimatter might be a better way to store energy than other technologies we have available on Earth?
Well, it turns out that even at the production rates of Fermilab at 2 nanograms per year, if you translate that into a medical therapy, that's enough for tens of thousands of patients a year. So at much smaller production rates, you're already producing enough antiprotons to treat cancers. And in fact, the reason I left Fermilab in 2000 was because the company that hired me away wanted me to work on cancer therapy using antiprotons. Okay, and those experiments, as far as I know, are still going on at CERN. though they can't produce enough antiprotons to treat a patient. But it turns out that it's a far superior way of treating tumors than proton therapy. And so you need a lot less radiation. Instead of 30 treatments spaced out over 7 weeks, you only need 1. So now you could actually do maintenance, and you can go after metastasis. If you have a targeting system that looks for metastatic sites, for instance, gold labeled molecules that link to the cancer cells. And so there are a lot of applications on the medical front. Then there also epilepsy, using this as a targeted probe to deaden one region in the middle of the brain without affecting adversely the other regions around the brain. So for instance, if you're an infant below 1 year old, they can't do radiation therapy if you have a glioma, brain tumor, because you get half the IQ that you normally would have had. That's how much damage the radiation from proton therapy does to the brain, to the infant brain. In this case, you would have no damage, or very, very much smaller damage. And then, okay, so the other thing you could do is Homeland Security sort of scanning cargo containers for hidden nuclear materials. So it turns out that the same, so what you do now is you annihilate the antiprotons with hydrogen gas. You form a pulse of pions. The pions also induce fission in transuranic materials, and then you look for delayed neutron back. So you have basically a radar system now. So you put out an output pulse and you look for a return pulse.
Thank you. I hope that can further motivate funding agencies to put money into this. There's loads of applications.
And once we actually have the antiprotons available, I'm sure we'll find many more.
All right. Well, seeing no more questions and no more hands raised, I'm scanning the chats and looking. I guess I will call it end. Thanks.
If anybody, I had my email address up there. I had my email address up in the first slide. If anybody wants to contact me, feel free.
All right. Thanks a lot. Bye.
Thank you.
Bye-bye.
Bye.